And welcome back to another lovely day in Thailand, same as the day before. I don't want to gloat about that too much anymore, but today we're going to talk about CAN, Controller Area Network. And ASF4 has the capability of talking to CAN devices on the CAN bus, and my chip, the C21, has the capability of driving a CANbus chip. And that's all down deep in here. The C21 talks to this CANbus driver, which then writes CANbus data on these two pins. Reads and writes. The driver handles, the electrical signals, which is a differential signal between the two pins. And then the chip and this the microcontroller and the CANbus driver simply exchange the packet data that has been decoded off the wire, and then my code inside the microcontroller does its thing. And the whole reason this board exists is to measure current and voltage and send the data out the CAN bus. This is the last major thing that I'll be focusing on for the board. So let's go play with Atmel Start and see how we can configure the chip. Okay, here's the state of the circuit board as I designed it. We have our CANbus chip over here. The receive pin goes to an LED that's supposed to light up when the receive pin is driven high. We'll see if that works. We come over here. The CANbus receive is on SIRCOM 1, pad 1, and it comes into pin 18, which is mapped to PA17. The transmit pin also has an LED, which should light up when the pin is driven high. And it comes over here. It's pad 0 of SIRCOM 1, pin 17, and PA16. Now, is this going to work in Atmel Start? I don't know. Let's go see. And you can see here in the chip's pinout specification that this is what I used to come up with the design on my circuit board. SIRCOM 1, pad 0 is PA16, maps to my pin 17. SIRCOM 1, pad 1 is PA17, maps to pin 18. And here we go. Add software component. Search for CAN, and the drivers are always down at the bottom, so we're going to add one CAN. I'm going to add it. Okay, we definitely want to use the async driver because that's all it's giving us. Well, here's a problem. It only wants me to use pin PA25 for receive and PA24 for transmit. So that's a problem. Let's go down and see what else I have to choose from. Now, CAN, you would think, is put some bits on a bus and read some back, but it's actually, once you open this can of worms, it's pretty complicated. But hopefully we can leave a lot of the things at their defaults. So we're not going to be worrying about timing and pre-scaling, FIFOs. We can play with that a bit later if we need a first in, first out buffer for our receiving data and transmitting data, filtering. Filtering and masking is very important in the CANbus world because say you've got a car with 1,000 CANbus devices in it, everything from a blinker light to the main motor controller. There's a lot of traffic on the bus, and you don't want your software to be responding to everything that comes on the bus and saying, is this something I care about? Is this something I care about? Is this something I care about? So you can apply filters which at the hardware level, it will mask out things you're not interested in and therefore only pass notifications into your software that, yes, this is something that you care about, then you can perform your action without a lot of extra overhead. So for now, we're going to leave all of this stuff as is, and that's really all we get to choose from. We're going to go look at this PA25 and PA24 situation on the chip pinout. Okay, we're back here at the chip. We're looking at PA25, which is right here. That comes over and it maps to CIRCOM3 pad 3, and PA24 maps to CIRCOM3 pad 2. Never in a million years would I have suspected that my CANbus would be restricted to the secondary pad set on the 4th CIRCOM device on the chip. But luckily, this maps us to pins 23 and 24, which luckily are right here, and they're not in use. And they're on the same physical side of the chip as the pins I'm already using, so it shouldn't be too horrible to move these across, although my blinky is going to have a bit of a problem, but that's a problem to be solved later when I redesign the circuit board. So what this means is I'm going to make the selection back in Atmel Start, regenerate all of the provided code, and hack my board to change to these 2 pins right here. And I'll get back to you. Okay, surgery complete. I cut the traces to the 2 pins on this end. Luckily, I could jumper over from the end of this resistor to the pin, and then the other pin goes down through a via. So the soldering was easy on this end, and then micro soldering onto the pin as usual on that end. But look at this. Look what I've had to do. This is the difference between a pure system and the restrictions that Atmel Start puts on your design. So that's a big lesson learned right there. Okay, I wanted to take you into the auto-generated configuration code, and you can see here this is the main system init that gets called for me, and it initializes all the devices that I've configured inside Atmel Start. There's my blinky LED, there's the ADC 0 and 1 flash timer USART for the USB bus, the delay driver, and it's added a new one, CAN0 init. So we go to CAN0 init. It's calling one of the low-level hardware routines to set some kind of a clock, and another low-level routine to set some other kind of clock with some gibberish here that would be extremely difficult to understand and get right. Then it initializes the asynchronous CAN driver with the symbol CAN0, which I will be using later on in my code. And then it calls CAN0 port init, which is yet another defined function right here. And all this does is it sets the pin function for the 2 pins defined for our use. So PA25 becomes our CAN0 receive pin, and PA24 becomes our CAN0 transmit pin. At this point, it's good to have a bit of a briefing in the background about what we're actually trying to accomplish. So I've been talking about CANbus a lot, but CANbus is basically the wire protocol where 1s and 0s are sent across the CANbus. But if you look up the logical stack of what we're trying to do, we're trying to send recognizable, usable data across that bus. And there are several protocols that are defined that sit on top of CANbus. The one we're interested in is OBD-II, Onboard Diagnostics version 2. This is used in the vast majority of modern cars in the world, and the commands and responses are all geared to what's going on with the vehicle. But luckily, I'm only dealing with amps and volts, so I don't have to worry about things like fuel pressure and the oxygen sensors. So let's figure out what we need to do inside the OBD-II protocol so that other devices on the CAN bus in the car can actually read and interpret my values. Now, OBD-II is vastly overcomplicated and is insanely highly detailed, and this thing works in this situation, but if you're on here in this mode, then this thing means this. It's a nightmare. Could have only been designed by an electrical engineer, because a programmer would never lay out the protocol this way. Plus, it's standards-ish. There are some well-known, well-defined values in the OBD-II protocol, but then car manufacturers are allowed to have their own proprietary ways of reporting data on the bus. And if you want to get that, say for Mercedes or some of the other cars, you get to pay them money, like $10,000 a year, to get access to their codes, which is one of the things that the right to repair movement is trying to get rid of. So, sorry about that little rant, but what do we need to know about OBD-II? OBD-II is a request and response based protocol. Ignore everything I previously said about broadcasting on the bus, like here's your voltage, here's your voltage, here's your voltage. No. A device on the bus has to ask my board, what's the current voltage in amps right now? I see that request, I respond back with my data. So it's request and response. That minimizes traffic on the bus, and it also can help with power consumption because the device can sleep between responding to requests. Like a device that's not used very much, like say an airbag, only has to do one very important thing in its life. So now if we scroll down here, we can see that there's this thing called a service, then there's a thing called a PID. So let me get down to that. Services, there are 10 defined, but we only care about one. Service 01 is give me the current data. This is real-time data of what's currently happening in the vehicle. We don't care about any of this other stuff. This is data that's been stored from previous runs. It's trouble codes. If you ever get the little flashing thing in your dashboard that says engine trouble, the DTCs is what the mechanic is going to check for because the car has detected something wrong, has logged a DTC, and then his little tool can read it back out. We don't care about anything else here. We are service 01, and that gets encoded in the request. Now, PIDs. PID, I normally think of it as process ID, but I don't even know what the acronym here is. But a PID is basically a numeric token that says, what's the value that I want to query? And you can see on this side here, the PIDs are listed both in hex and decimal, and how long the data is expected to be. And there's a lot of them that are predefined, all the way up to C4. And manufacturers are expected to provide these values and query for them when they are able. And you can see, like this is long-term fuel trim bank 1, and it gives the expected minimum and maximum values and how you actually calculate the real value from what the CAN data is going to be providing back. Like engine RPM could be anywhere between 0 and 16,383.75. And the way it's calculated is it comes back as two distinct numbers called A and B. A is considered the high part of the number and B is considered the low part of the number, because with OBD-II and CAN you have to slice it up into 8-bit bytes.
So you take the high number, you multiply it by 256, and then you add the low number. You have now reconstituted the engine RPM, but it's also scaled by 4, so you need to divide by 4. Then you have the vehicle's actual RPM. Okay, let's scroll down to here, and we look at PID 9A, Hybrid EV Vehicle System Data, Battery Voltage. That's pretty close to what I'm trying to provide. Not just voltage, but voltage and current. I cannot find anywhere in the predefined set of PIDs that has anything to do with current flowing through any wires. So I'm going to use 9A, and I'm going to hijack it for my own use. And, I'll document exactly how I'm going to provide the data for any of the devices that want to read me. And it's just the best fit I can find. Okay, let's take a look at how CAN request and response messages are constructed. The first thing that a CAN request message does is it sets up the outgoing ID. The normal CANbus ID is 11 bits long. There's also an extended CANbus ID, but we're not going to worry about that. The normal request ID is 7DF hex. Now, devices can see this come along the wire, and then they look inside the packet for the PID. And if they see their PID, then they respond to that. Devices respond with a CAN ID in this range, 7E8 to 7EF. Now, 7E8, this range is not very well defined, other than it kind of generally allows 8 CANbus computers inside your vehicle to be on the bus at the same time. They all get assigned their own ID. I'm going to skip 7E8 because that would be the primary CAN device. So I'm going to go with 7E9 as my response ID. So here's the response structure. I'm going to respond back with a CANbus ID of 7E9. And then what you also have to do is you take your service number, which comes across, which for me is 1, if you remember above, 01. You add 40 hex to it, and you put that in your response packet. So that says, 41 hex says, I'm giving you current data right now. And then I give back the same PID code as was sent to me, and that's my 9A hex. And then I'm going to be using 1, 2, 3, 4 values to send back the voltage and current in the system. Then when the receiver sees my packet come across, they extract these, and Bob's your uncle. You've got voltage and current. Here's another helpful website that kind of shows this pictorially. The request is 7DF, 2 bytes of length for the data, mode and service 01, and the PID is 0D. That PID means what's the vehicle speed. The vehicle speed computer responds back with 7E8. I am a CANbus device and I'm responding to you. I'm giving you back 3 bytes. I've changed my mode to 41. I added 40 hex on. I'm giving you your same PID back, and your value is 32. 32 hex is 50 kilometers an hour.
Okay, we're initializing the CAN bus. I set up my 3 callback methods. I only want to filter on the standard ID of 7DF, and this magic number here says basically ignore anything except for 7DF. I set that as my filter for a standard ID. I enable the CAN bus, and then I initialize a timer that I'm going to use in debugging. Okay, we initialize a timer that fires every second, and this is purely for debugging, to send the value onto the CAN bus so I can try and look at it with the oscilloscope. Okay, here's where I send our sample message over the CAN bus. I set up our buffer, I set up fake data for volts and amps with the numbers A, B, C, D, A, B, C, D, which should be recognizable on the oscilloscope. I say we have 7 data bytes. We're responding to someone's message, so we're in 41 is our service. I'm sending back the same PID they sent, which should be 9A, and I'm setting up the bytes for the least significant and most significant byte of volts and amps. The least significant byte, by ANDing this, is going to give us CD. Shifting by 8 is going to give us AB. So it's CD, AB, CD, AB. We send our ID for the whole packet. We're saying it's data. Our data is going into the buffer, length 7 again. It's a standard, and we write it to the bus. Okay, let's flash the code to the board and watch what happens on the scope. Building. Succeeded. And we are over here. We have some CANbus data, but it's gibberish. And I know I'm set up for 500 kilobaud. It's not capturing anything. Oh, the pain.
As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.